So I thought I'd go through the four examples from the booklet that involve three-dimensional questions. The first example is looking at a vertical mast being supported by two cables from points A and B. So basically the question is requiring that you find the height of the mast, which is that side there, correct to 3 decimal places, and then it's asking the angle of to the horizontal of the cable from point B, so this little angle in here. So the easiest way to do that is to split this question into two triangles. The first triangle, you see you have got an angle that you know, which is 48 degrees, and a side length which is 36 meters, and an unknown side which you would then calculate. So when it's a three-dimensional problem, you need to reduce the problem into a two-dimensional problem and solve as normal. So for this one, we know something about the opposite side, which is x, and we know something about the hypotenuse, which is 36 meters. So the ratio we would be using in this part of the question would be opposite and hypotenuse, which is sine. So sine of the angle 48 degrees is equal to the opposite over the hypotenuse, so x over 36. And you would just then use your calculator as usual, menu 36 to get the numerical solve, and then we would type in obviously sine of 48 is equal to the fraction template and x over 36, and we solve that for x. So on our calculator there we can see that the height of that pole or the mast is 26.753 meters, correct to 3 decimal places. Now the biggest hint with questions like this one, where we need to actually use a side length calculated in part A to calculate something else in part B, the idea is not to round. Even though the question told you in part A to round to 3 decimal places, you round to 3 decimal places for your actual answer for part A, but then if you're calculating part B using that answer, you don't round until you get to the end of part B. Okay, so part B has a different triangle, so we'll just redraw that triangle on our paper so it's a little easier to see what's going on. We have an unknown angle at the bottom there, at angle B. The base of that triangle we can see is 24, and the height we just calculated in part A, the height of that triangle was 26.753. So in this question, to let the person know that's correcting your work, if this was a test or an exam or a quiz or something, and to let me know that you're not using the rounded value, you put 3 dots after the 3. So that basically shows whoever's correcting this work that the 26.753 is not a rounded value in your answer. Okay, so in this part of the question now we know something about the adjacent side, which is 24, and the opposite side. So now we're using the tan ratio, and I'm calculating tan of angle theta, and for my fraction opposite over adjacent, when I put that into the calculator, I'm going to put the whole value, that 26.753, and all the other digits that go after it. Okay, I'm not using the rounded value, and 24 I'm using the other value that they gave me. So when we put that one into the calculator and we do menu 36, when I start typing in that equation, tan of an angle, I'm just using letter A, tan of angle, A for angle, not AA, tan of A is equal to fraction template, and I'm going to actually use my up arrow to highlight that whole value and hit enter, and it puts the whole value into the part of the fraction that I want it, and then 24 is the the denominator, sorry, of that fraction. I'm solving that for A. I use, if you've noticed in the one above, I used X for a side length and A for an unknown angle. When I solve that one, 2 decimal places on that answer would be 48.11. And the unit would obviously be degrees. Okay, so that's example 1 done for you. Example 2 is a cube, but you can probably already see that there's a right angled triangle up on the top of that box. They're talking about an ant walking along the outside of a box, and it goes from vertex H across the box to vertex F, and then down to the bottom of the box, vertex B. So we can see that from F to B is 6 centimetres. And then I need to use my, probably Pythagoras is the easiest way to use this one, to answer this one. The triangle at the top of the box, HEF, with a diagonal across the box, would give me a right angle triangle. I know 2 of the lengths on the box, so I could easily use Pythagoras for this one. So it's basically, it's up to you, depending on what information you are given in the question. It may be a Pythagoras question, or it may be a trigonometry question, or it might be a combination of both. So from our diagram, from H to E to F on that box, I've just redrawn it as a basic right angled triangle. As you know, there's a right angle in the corners of rectangular prisms. So from H to E, you can see off the diagram is 8 centimetres. And from E to F, you can see also off the diagram that is 10 centimetres. And you can then figure out from H to F is going to be the unknown thing in the equation here. So we're going to be using Pythagoras because I don't really know anything about any angles in that triangle. I do know 2 sides, so it's easy to use Pythagoras to find the answer here. So we know that x squared is equal to a squared plus b squared. So we know 8 squared plus 10 squared. And when you calculate that on your calculator, because this is a normal solve, it hasn't got trigonometry in it, I can use menu 3(1) this time. Okay, and I'll type in that equation. X squared is equal to 8 squared plus 10 squared. And I'm solving that for x. So you can see there the equation has 2 solutions, a negative one and a positive one. Obviously this is an example using measurements, so I only am interested in the positive answer. The question tells me to go to 1 decimal place, so I know that the answer for the HF measurement, or the x measurement, the hypotenuse, is 12.8 centimetres. Now if you can imagine the ant has walked across the box from here to here, H to F, it's moved across the box 12.8 centimetres, and then to get down to the bottom of the box, it's walking another 6 centimetres. So to actually answer the question, the distance that the ant walks will be the 12.8 that we've just calculated for the triangle, plus the extra 6 centimetres that it walks down vertical on that box. So the total distance that the ant would have walked on that box is 18.8 centimetres.